She's the winner of the FSA prize, and she will talk about Cremona groups of rank at least 3 after.
Thanks.
Welcome.
Thanks a lot. So what are Cremona groups? Okay. For me, a Cremona group is just a group of birational maps of a projective space. Or some field. Okay, and then N is the rank. And sometimes you see, well, I'm gonna write here PN. Okay, for this. But what is a birational map for those who don't know? A birational map is an isomorphism between open subsets, Zariski open subsets of Pn, but more precisely, they are maps given whose coordinates are quotients of polynomials. So these are maps of the form maps. I'm sending x1 up to xn. This is in affine coordinates. To f0 of all these divided by g0 of the xi's to fn of the xi's divided by gn. Not the fn and the gi's are polynomials with coefficients in our base field. Now this is not a map everywhere. A priori, this map is not defined if one of the gi's is 0, or like they should not be 0 at all. But there are points where one of the gi's is 0, and then that's where the map is not defined. So that's why I'm writing map with quotient marks, and that's what I mean by this dotted arrow. It's not a map everywhere. And so a priori, that's a rational map. And by birational, I mean a map of this form that has an inverse of the same form. Since I can send xy to 1 over x, 1 over y. That's an involution. If I apply it twice, I get back the identity. I can choose a bit more carefully, like something like a1x plus a12y plus a13 divided by a31x plus a32y plus a33, and then a21x plus a22y plus a23 divided by the same that is here. And I just want that the determinant of the aij's is non-zero so that I can invert this map. So this is an automorphism of P2, but written in its affine form, right? And then I have a bit more complicated ones. For instance, I can act with a Möbius transformation on the first coordinate. and one a Möbius transformation on the second coordinate, but my coefficients will depend on the first coordinate. And for this to be invertible, I need A, B, C, D to be invertible, and I need alpha, beta, gamma, delta to be invertible. And here I can see that, well, the set of all these gives me a group, and that's PGL2 of K, and then semi-direct product with PGL2 of C of Y. I hope the semi-direct product is in the right direction, but I think it's a bit around. So this way you can see that the Cremona group of P2 is not at all finite dimensional. It's infinite dimensional, whatever that means. It's very big. It has, oh, sorry, this should be okay. And more generally, I study this group. I want to know properties of this group. So, and a very old question. So this group has been studied since I would say 1860s. I think the first book that was written on it was in 1862 by Luigi Cremona. And it has been studied on and off since then. Sometimes it was in passion, sometimes it was not in passion. And one of the questions that we find already in one of Enrique's books is whether or not this group is simple. That means whether or not this group contains normal subgroups. Sorry. Delta, they're in K of X. So they are quotients of polynomials in X. Well, and then, so in his text, he says that probably it doesn't happen. He just guesses this. He doesn't explain why exactly he thinks this. Different people have different theories why he thought this is the case. Let me give you my theory. Oh, I'm too close to I see. Okay. The reason is that it is not so easy to find normal subgroups. So the nicest elements that we know, well, these, for instance, when you try to compute the normal subgroup generated by one of these, you actually get everything. So an example of this is the following. So there are trivial from the plain Cremona group to a finite group. And the proof is actually is surprisingly easy. if you know a theorem that I've forgotten to state, but I will repeat it. So let's say we have subgroup homomorphism. In here, we've just seen there's the sitting the automorphism group of P2. That's this one. And it is isomorphic to PGL3 of C. That's infinite. This is finite. So at least one non-trivial element of this group has to be sent to 1. Let's say this is phi. So phi of alpha is 1. So that means the normal subgroup, the kernel of a homomorphism is a normal subgroup. And that means the smallest normal subgroup containing alpha is contained in a kernel. So the normal subgroup generated by alpha in PGL3 is in the kernel of phi. But PGL3 is also PSL3 because we are working over C. And that is a simple group. It doesn't have any normal subgroups. So this is actually PGL3 C. And now we have a sort of conclusion. There's a very old theorem by Noether and Castelnuovo. Its first proof was by Noether, but it had a gap that was built by Castelnuovo. And it says that this plain Cremona group is generated by, well, the automorphism group of P2 and this involution right here. And now we check that sigma is also in the kernel of phi. And in fact, the way to show that is to show simply that it is contained in the, contained in the normal subgroup generated by alpha. So, okay, let me do this. It's a straightforward calculation. We put H to be -1, 1, -1, 1, 1. If I got the minus signs right, this is an involution. And we have sigma after H to the power 3 is the identity. So this you can compute straightforwardly. What we get is that sigma is this. Sigma and H are both involutions. So actually we have this. So here we have something that is conjugate to an automorphism of P2, and then times an automorphism of P2. So this is in the normal subgroup generated by PGL3 of C, which in turn is in the kernel. Okay, and then that means all the generators are in the kernel of phi. So some repetition from group theory. All right, so just to say, it's not easy to find group homomorphisms. It's a bit, takes more work, but one can also show, this is a result by Ghisatulin, that all the elements that I wrote down, I should not. Okay. So all the elements of this form smallest normal subgroup generated by them is also the whole group. So really all the nice elements we know, they generate the the normal subgroup generated by them is everything. So these are difficult to find. So I think that's why Enriquez ventured that probably there are no normal subgroups. However, there are. So the first version of the theorem is from 2013 over C, and then over any field from 2015. And it says that here P2 over K is not simple, meaning that it has non-trivial proper subgroups. And Langeau even gave an example of this, and that's if we take the polynomial automorphism of an that is given by xy is mapped to y yn minus x, and the characteristic of our field K is not supposed to divide n, then this, a power of this, so there exists some n, at least one, such that the normal subgroup generated by this power is a proper normal subgroup of the Cremona. And the way they did this was by creating, so you blow up all of the points in P2. This is an inductive limit of neuron-series groups. And on this inductive limit of some neuron-series group, you can lift the intersection form of curves. And this intersection form is a bilinear form on this enormous space. And it cuts out a hyperbolic subspace of infinite dimension. And then you can do geometric group theory on it and create normal subgroups. The only issue is that this doesn't generalize easily into higher dimension because, okay, you do have intersection of divisors and curves, but you cannot construct this hyperbolic space this way. You have multi-intersection forms of divisors, but also this doesn't give you a hyperbolic space immediately. So this is their technique is not a direct way to generalize this to higher dimension. Interrupt me if you have any questions, by the way. All right, so. Now, we may not be able to just come up with a normal subgroup or in other words, we cannot just come up with a quotient of the Cremona group that is reasonable, but we can come up with quotients of subgroups. So let me see. Let me introduce an interesting homomorphism. At EGL2 of C of Y. Okay, so we look at, this is the map, this is the group that does mapping on the first coordinates, and then this alpha. Okay, the y under bar is just y1 to yn. Okay, so this is the group. Okay, alpha delta beta gamma is not 0. Okay, and they're still regression functions in the yi's. And we can check a determinant. Only that the determinant is not really well defined, right? It's PGL2, so it's a determinant that makes only sense if we take out squares. And now this, we can actually write it in some fun algebraic way. This is a sum of two sets where I sum over all prime divisors. I have of Tn. So here, if I take, so how does it work? I take the class of some element in here. It's a quotient of two polynomials, and I can factorize them into prime elements. Instead. And now I can just map this. So each of those gives me a prime divisor. I can just map this onto, all right, so I'm modding out the squares. So this means the AIs are actually 0 or 1. And I can map it to the EIs. And I sum over the prime divisors by the alpha. So this is, let's say, so what this does is the following geometrically. This birational map contracts some curves, some subvarieties, and it's a diffeomorphism at all points where the differential does not vanish, and where the differential vanishes, that's big. Something happens to the tangent space, right? It gets collapsed. So actually, the differential. Let's say this is f. So the determinant of the differential, where it vanishes, that's exactly the set of all subvarieties of Pn plus 1 that are contracted. It is more or less the determinant. So what this morphism counts is more or less everything that is contracted, but just up to parity. So what we showed. That there is a projection of this sum onto a subset of prime divisors, such that I can lift this homomorphism to the whole Cremona group. So here, this is for dimension n plus 1. So for any two, this group homomorphism. corresponds to a group homomorphism. Plus 1 to Z2. It's homomorphism, so composed with some projection I. And here's I. And I is uncountable. For any n, maybe I should add this. There exists some I subset of prime divisor. Okay. Now the statement is more. Okay, and in particular, this group homomorphism is surjective. Okay, it's not trivial, it's surjective. And in particular, the Cremona group, high rank, also has homosexuals. Okay, so what I want to do is just say a few very loose things about how we prove this. And then I want to say a few words about new results that have emerged since then that use a similar technique that are not my results. So how do we construct group homomorphisms in our bachelor? We have a group. Usually we have a group where we know generators, we know relations, and then we construct a map and we check that all relations are set to 0 or 1. And then we have a group homomorphism. The issue with that for us is that starting from P3, we do not know any reasonable generating set of the Cremona group. So we know one for the plane Cremona group by the Noether-Castelnuovo theorem, but we do not know in higher dimension. Like the simplest we know is everyone, is the whole group. That's the simplest set we know. But then there's a very old trick, and that's to embed the group into a bigger group that you know better, where you know generators and relations. Okay, so now we put it into a larger group, G, where we know, oh, here. We construct our homomorphism from here. And then we show that the restriction is not trivial or is surjective. Now for us, the group is a priori a lot, it's not even a group, it's a groupoid. Okay, so I'm going to tell you what it is. So this is the set of birational maps between so-called Morris hyperspaces. that are birational to Pn. Let's say rational Morey fiber spaces. So this is a Morey fiber space is something that has a fibration to a smaller dimensional variety. So if this is dimension n and this is the dimension d, then d is smaller than n. And the anti-canonical divisor is relatively ample, so on all the fibers it is ample. And it has nice singularities. And the relative Birkar rank is 1. So these are the terminations of the terminal objects of the MMP. So this is not necessarily a group. We can invert, but not necessarily compose. Right? So this morphism here is a priori a morphism between groupoids. And then when we restrict it to a subgroup, it becomes a homomorphism. And here, by a result of Haken and McKerner, we know a generating set. The generators are so-called Sarkisov links. And we provide a set of generating relations. And then we use these generating relations to construct this map. So another thing that was very crucial was the boundedness of Fano varieties, proved by Birkar, because the relations we have, so let me say, right here, this is generated by so-called Sarkisov links. We call it that way. I'm not going to give a definition of either. I think it's too long. But more or less, the idea is that Morey fiber spaces have relative Birkar rank 1. Links correspond to fibrations that have relative Birkar rank 2. And elementary relations correspond to fibrations that have relative Birkar rank 3. So if we have an elementary relation and we resolve it, we get some sort of, let's say, some sort of fibration with relative Birkar rank 3. And what we know is that if we are given a curve in this space, its preimage in T has to be Fano. So this means when I resolve all these maps, in order for the fibers to stay Fano, I cannot blow up things that are too complicated. Okay. Because of the boundedness of Fanos. So we can say exactly among certain type of relations how complicated are the things that are contracted in the maps in these relations. So we can compute certain relations exactly, and then with this we can construct the morphism. Okay, this was very hand-wavy, but I wanted to mention it because it's still very crucial. It does, but the way we do it, it gives you the trivial homomorphism. Because for n equal to 2, all you contract are rational curves, and those are exactly the ones that we send to 0 also in higher dimension. We send to 0 a lot more. But there's a theorem by Julia Schneider who adapted the strategy to dimension 2 over perfect fields, where you contract more than just rational curves, and then this actually works very well. And so I want to say this. You could do her theorem by really adapting it, but she found a way to prove it independently of what we did. So it's really elementary with linear systems. Practice. From 2021 as well, but I'm not sure anymore. This is for any perfect fields. This is reflective morphism from here to the subsum of two sets. It's projective. And here I has the cardinality, at least of the. So if your field is Q, I is going to be countable. So up to a certain moment, all our strategies that we had to construct quotients of the Cremona groups ended up, oh my God, I'm sorry, this should be a set two set, sorry. Ended up in set two sets, and we were wondering like what this was all about. But there is actually not a lot of reason for this. Like this is really something that depends on our choice of construction, because with similar techniques as the one we had, we can now construct group homomorphisms to free products indexed by Z. No, it's the same one as the one from over there, and then it's in skip. I'm gonna two. There exists a surjective group for any and at least four. There exists a surjective homomorphism from the Cremona group. Free group. Indexed by Z. So this gives you an idea of how big Cremona groups actually are. Like almost like any group I can think of is a quotient of a Cremona, basically. Yeah, so they also, in the same paper, they have one that goes to a free group of sets. And I think is countable. The way they did this is they looked at Mori fiber. So we looked at Mori fiber spaces. We looked at relations among Mori fiber spaces that are conic bundles. And what they did is look at Mori fiber spaces, or relations among Mori fiber spaces, whose generic fiber is a Savary-Brouwer surface. The birational maps of a Savary-Brouwer surface are very easy to see, since the Savary-Brouwer surface has only points whose degree is a multiple of 3, so they're very nice. And they use the geometry to construct these maps. So at the time when they announced the result, there was a race going on. Usually there are not, I think in my tiny field, there are not a lot of races. People are more collaborative than competitive. But there was somehow a race going on because there was a group, Lind and Schindler, who published their result. In the end, so they announced it very, like in 2019 or something. They announced it in 2022. They published it in the same year, but they published it a bit before they did. So there is a surjective. These 4 use a surjective homomorphism from the Cremona group to a free abelian group. And that's the free abelian group generated by the isomorphism classes of varieties of dimension m-1. This is somehow the Grothendieck ring of varieties. And it is I don't know if it's surjective. But basically what they do, so they have a completely different approach. So if you have a birational map of PM, you look at what is, so let's say this is phi, and where do you map phi to? You look at all the divisors that are contracted, and you take their sum. And then you do minus all the classes of the divisor that are contracted by the inverse. And they show, this is the easy part, this is not the most difficult part of the paper, but they show that this gives you a group homomorphism. And then to show that this group homomorphism is not trivial, you need to do stuff. And what is the crucial part of it is an example by Lamy and Hassett. That is an example of a birational map from P4 to P4 that contracts exactly one hypersurface in each direction, and the two hypersurfaces are not L equivalent. So this way, they know they have at least one map that is not sent to zero here. And that's how they construct it. Okay, so this is a totally different approach. Well, and the two theorems kind of leave open the question, what about m equal to 3? Like, can we get homomorphisms to Z? Or Z mod 3? Or other nice abelian groups? And we have no clue for the moment. But if you're interested, feel free to try out. And that's all I wanted to say. Thanks a lot for the attention. Sorry, this? Because so the smallest dimension where we have an example of such a birational map is 4. And then to get higher dimensions, you just go across P something. But we don't know it for 3. We don't have an example so far. If we had one, this would be, we could basically use their homomorphism and add it and then paper done panels. So the homomorphism is a homomorphism for any dimension. It's just that we don't know whether it is trivial or not for dimension 3. here. You need, so wait, to construct a principal ideal and what is this? I need to do. I don't know, but I think they should try it. Oh, right. Because, oh, right. So for if you have dimension 3 and you look at a Severi-Brauer vibration, that doesn't, sorry, I want to say a lot of words, so let me write it down. Here you have P3, you go to a curve, the generic fibers are surfaces, but there's always a section because that's a curve by Zen, I think Zen's lemma. And so the fibers, even if they are forms of P2, they always have a rational point and then they are P2s. So the construction uses non-trivial Severi-Brauer surfaces. I mean, I wasn't born in 1895, so. I don't know how to answer the question because some time ago, but I think different schools have been working on the questions during different moments when it was fashionable for them. For instance, I know that at some moment, I think maybe during the 70s, there was a Russian school trying to work on it. And I was told that they were very divided. There was one fraction that was like, yes, there are normal subgroups. And another one that was like, hell no, there are none. And they were kind of working in different directions. So I think people worked on it on and off, but I do not have any concrete results that where I could point out that people were working on it. So the earliest result that I can say was published in 2013. That is the theorem of Cantat and Lamy, that there are normal subgroups in dimension 2. Yes, all the theorems that are here are on arXiv. Yeah, all of them.
Question, let's let the speaker again.